Hello, my name is Adam Ruthford. I'm here to talk to you about electric power forecasting in Texas, and we're using January 2021 for this study. Electric generation comes from several different sources in Texas. We have renewables, we have coal and gas, we have nuclear. Your demand is cyclic in nature on both a daily, weekly, and annual periods, and it's driven largely by weather conditions. Accurate models of demand are necessary so that we can ensure we always have plenty of power available. Inaccurate models of demand, though, can cost money because unnecessary standby power might be required. For this study, weather data was obtained from the NOAA. 10 locations initially were selected and sampled in Texas. This example is from Arlington. However, there were problems with the weather data. Single instances of missing data were just simply used fill, the function to fill them down. However, two of the data sets had many hour stretches where no new data was posted, so they were discarded. This example on the right is from Longview. The flat runs show us where the data was missing. Power generation data was obtained from ERCOT. Initially, the power data was not very user-friendly. It was organized by row for each day and fuel, with separate columns for each 15-minute increment. This was changed so that each row represents 1 hour in the month, and there are separate columns for each type of fuel plus one for total. All amounts are normalized to megawatt hour. If we look at our realization in our ACF, we see a definitely 24-hour cycle on both the realization and the ACF. Power data, as I said before, is expected to have annual, weekly, and daily periods, and over long enough time frame, it does follow an airplane type model. So first, an ARIMA model was fitted. Recognizing that we have a 24-hour day, S equals 24 was first indicated. Recognizing also that the model does tend to randomly move, there's some wandering behavior. Initially, a D equals 1 model was tried. However, results were very unsatisfactory. It quickly departed from the actual realization by a great amount. So looking at the S equals 24, both the AIC and the BIC, looking at the residuals, they both indicated an AR3 model would be appropriate. Here you see the final model down below. So the ARIMA model still did not filter out all the white noise. The young box test had a very small p-value, so the null hypothesis was rejected, as well as the ACF, as you can see in the lower left-hand corner, has definite spikes at hours 23 and 24. On the right side, we can see our forecast. The forecast is in blue. For both the short term and the long term. A VAR model was tried. Actually, 2 different VAR models were tried. The first one uses an average of the explanatory variables, the temperature data, as the explanatory variable. The second one, we treated the 8 temperatures as different variables. If you look at the 2 realizations, the blue line represents the 8 different variables. The red line is the average. The average performs superior to the 8 distinct locations in both ASE and forecast suitability. You can see you actually get a period with the average, whereas you don't really get that with the 8 different variables. Next, I tried a neural network. Tried several different HD parameters, but I found very little difference in the ASE with different HD parameters. The realizations, or the predicted realizations, didn't change much. None of them were very accurate, so for the purposes of this, I just kept the default parameter for HD. Lastly, I tried an ensemble model, both short and long term. The AR3 and the VAR temperature were the 2 most accurate models. So for this, the ensemble, we use those 2. We can see down here on the left, we have our ensemble with in green, the actual realization in black, and then the AR3 in red and the VAR temperature in blue. And that's also on the right hand side, so we can kind of see what that looks like. So, conclusions. The two best performing models overall are the AR3 and the VAR with the temperature, average temperature. The ensemble model created from those two was created from those two. And judging by graphs and ASC, in the short term prediction, the ensemble model performed best. Long term, it was actually the VAR average temperature model performed best. You can see the ASC over here on the side in this table. So here's our short-term ensemble model, including the prediction limits. All right, we can see it fairly closely tracks. And here's our long-term one-week model. We can see the limits again in red and the actual model predictions in blue. And we can see that there's some difference between things. It doesn't pick up that wandering behavior in the actual realization, but overall it does a decent job of predicting when it goes back to sort of a mean. Thank you for your time. Good night.